Hello everyone. I'm going to share a configuration in geometry that intrigued me. Concurrencies are one of the most eye-pleasing encounters in geometry for me. Today we will take a deep dive to explore a beautiful concurrency in quadrilaterals. Before diving into the actual configuration, let's quickly learn some of the prerequisites for the exposition. First, angles are preserved upon scaling. Second, angles subtended by the same arcs are equal. Here the angle subtended is considered on the other arc of the underlying circle. Let us take a closer look at each of these. Scaling can be thought of as a zoom in or zoom out that we are aware of. Scaling is done about a point on the flat plane, say P here. Then, selected objects are considered for scaling about P. Here we consider a square and a circle. We transform each and every point on these objects to a desired point along the line, joining it to P as per the scale factor, starting from 1. For instance, this is how it looks when we scale down the objects with 0.25 scale factor. In order to bring it back, we may rescale the objects 4 times to the original scale factor of 1. Alright, let us now consider an angle in the plane far away from P scale down the angle to get a new angle image. Notice that the corresponding set of lines of this transformation are parallel due to the same scale factor being applied to all the points on the object, and so the results follow by the basic proportionality theorem. This means that both the angles thus formed must be equal because they are formed by a pair of parallel lines. Okay, next, angles subtended by the same arcs are equal. Consider a circle and an arc of the circle shaded in green. The angle subtended by this arc on any point on the other arc is the same. That is, the value of the angle theta is preserved over all the points on the other arc. This property is true irrespective of the size of the other arc under consideration. This is due to the fact that the angle subtended on the center of the circle is twice the angle subtended on the other arc. This is known as the inscribed angle theorem. The converse of this theorem is also true that the points are concyclic if the angles subtended on the same side of a segment are equal. Consider a quadrilateral, maybe convex or concave, but let us consider convex quadrilateral for this discussion. Let the vertices be labeled as A, B, C, D. Consider the 4 circles formed by choosing some 3 vertices of A, B, C, D. That is, circle BCD, circle CDA, circle DAB, circle ABC. Each of these 4 circles are then scaled down with a scale factor of 0.5 about the vertex that is not on the circle. For example, the circle BCD is scaled down about the vertex A with 0.5 scale factor. Similarly, all the other circles can be scaled down. Considering all 4 smaller circles, we observe an astounding configuration. All 4 circles concur at a point, say K, and not only that, the 2 adjacent circles concur on the sides of the quadrilateral, which is also the midpoint of the sides. Call the top left one as the first small circle, the top right circle as the second small circle, the bottom right one as the third small circle, and the bottom left one as the fourth small circle. Let us first understand why the smaller circles concur on the midpoint of the sides, and later we will prove the concurrency of all 4 circles. Consider the circle BCD. Reducing it with a scale factor of 0.5 about A brings vertex B to the midpoint of AB, that is MAB. Similarly, the vertices C and D map to MAC and MAD respectively. Similarly, the circle CDA, upon scaling down about B, contains MAAB, MBD, MBC, which explains the concurrency of these first 2 smaller circles at MAB, the midpoint of side AB. Now, a similar argument can be put forth for the concurrencies on the sides. Though we did not prove the concurrency of all 4 smaller circles, let us get started with that proof. Consider the angle BCD, which is angle C, along with the circle BCD, and scaling it down to the smaller circle will preserve the angle, and thus Angle MAB, MAC, MDA equals angle C. Similarly, with the angle DAB and circle DAB, we scale it down about C and we get angle MBC, MAC, MCD equal angle A. Define the point K to be the intersection of these two smaller circles. Since the angles subtended by same arcs are equal, the angle MAB, MAC, MDA equals angle MAB, KMDA, which is subtended by the arc MAB, MDA, and the angle MBC, MAC, MCD equal angle MBC, KMCD, which is subtended by the arc MBC, MCD. Let us now prove that the other two smaller circles pass through K. We now try to chase the angle MAB, KMBC. Suppose if we are able to prove that angle MAB, KMBC equals angle D, that is angle CDA, then by scaling it with a scale factor 2, it preserves the angle and it equals the angle ADC. Thus the points D, A, C, and the new scaled-up point of K are concyclic by the converse of the inscribed angle theorem. Scaling this circle with 0.5 scale factor about B would mean that the smaller circle passes through the points K, proving the desired result. Similar analysis for the other small circle yields the required result. Thus our to prove statement is changed to angle MAB, KMBC equals angle D. Suppose the operation of scaling the first smaller circle back to the circle BCD with scale factor 2 takes the point K to A prime on the circle BCD. Similarly, scaling the third smaller circle back to the circle DAB with the scale factor 2 takes the point K to C prime on the circle DAB. Observe that the quadrilateral AC, A prime, C prime is a parallelogram because the diagonals bisect each other as the scale factor was 2. Hence, the sides AC prime and CA prime are parallel. Therefore, the sum of interior angles C prime AC and A prime CA is 180 degrees. Dissecting these angles into 4 angles, we obtain angle C prime AD plus angle DAC plus angle A prime CD plus angle DCA equal 180 degrees. Moving angles DAC and DCA to the other side of the equation, we get 180 degrees minus angle DAC minus angle DCA, and by the angle sum property in triangle ADC, it equals the angle ADC, and that is angle D. So, we get the sum of angles C prime AD and A prime CD as angle D. Consider the circle DAB and C prime as a point on it. Thus, the angle C prime AD equals the angle C prime BD, as they are subtended by the same arc C prime D. Similarly, in the circle BCD, angle A prime CD equals angle A prime BD. Thus, considering their sum, angle C prime BA prime equals angle D. Now, in triangle ABA prime, we have KMAB parallel to A prime B by the midpoint theorem. Similarly, in triangle BCC prime, we have MBCK parallel to BC prime. Thus, the angle MABK-MBC equals the angle between A prime B and BC prime, which is angle D. This is due to the angle between same set of parallel lines. This proves our required result that the second small circle passes through the point K. Now, we have found measures of 3 of the angles formed by the midpoints at the point K. What about the fourth angle? Notice that the sum of angles of a quadrilateral is 360 degrees. Thus, angles A, B, C, D add up to 360 degrees. Hence, angle B equals 360 degrees minus angle A, minus angle C minus angle D. Since 360 denotes the whole angle, we get angle MCDK MDA to be equal to angle B. Following similar proof as that of the second small circle, we get that the fourth small circle also passes through the point K. Therefore, all 4 small circles pass through the point K. Let us meet in another beautiful video. Until then, stay tuned and happy learning.